there are many different ways to find enthalpy. One way is to use the bond energies, where you break the bonds of the reactants and they subtract breaking the bonds of the products. A second way is experimental. A third way is Hess's law. And we are going to learn the fourth way, and that is to use some values that are looked up or that are given to you. And we're going to find that delta H by taking the sum of the products and subtract the sum of the reactants. And I know it looks a little bit weird comparing it to bond energies, but remember with bond energies, you have to break the bonds first and then you have to form the bonds. So that's why it's opposite of this way that I'm going to show you. Let's start off with an analogy. Let's say I give you $100 to play the stock market, and after a week you go to look at those bonds that you invested in and you find that they are not worth $100 anymore. Now they're worth $150. So what is the change in value? The delta means difference, and so you're going to do final minus initial. So I have $150 minus that $100 I put in, and I get a positive $50 that I earned. We can apply this to chemistry. Let's say my reactants in the bonds, they total 100 kilojoules per mole. And then let's look at our products, and let's say our products, they are 150 kilojoules per mole. Well, what is the change in energy? So I'm going to do final minus initial, and I get a positive 50 kilojoules per mole. This is an endothermic reaction. If I were to sketch this out, I would see that my products are at a higher energy than my reactants. So I've actually gained energy here. So with the difference being 50 kilojoules per mole. Let's look at another analogy. Again, I give you $100 to invest in the stock market, and at the end of a week you find that your stocks are not worth $100, but now they're worth only $50. So what's the change in value? Again, do final minus initial. So 50 minus 100, I get a negative 50. So this is the money that I lost in the stock market, and we can apply this to chemistry. So we can look at our reactants and look at the stored potential energy in the bonds, and let's say it's 100 kilojoules per mole. And then we can look at our products, and let's say it's 50. So final minus initial, I get a difference of a negative 50 kilojoules. Now this doesn't mean that I have negative energy, it just means that this is the energy that's lost. So this is an exothermic reaction. If we were to sketch this out, we would see that our reactants have more energy than our products, and the difference in that energy would be 50. And this is delta H, or enthalpy. Enthalpy is given the symbol of H, so that H right there in the middle of the word enthalpy reminds you that we are finding the delta H, or the enthalpy, or the heat content. And we will be given values of the enthalpy of certain compounds, and we'll be able to subtract them, products minus reactants, to find what the delta H is. So enthalpy is the heat content of the chemical. Enthalpy is an extensive property, so that means the number of moles you have, that's important. And you are going to be given enthalpies of formation to find your delta H. You could be given them through Hess's law, but you are going to take your products and add them up. So this symbol right here, this is your sum, or adding up the values. And they're called heats of formation, so it's like an H sub F. So just know that they are numbers that have been determined experimentally, and you're going to add them up for your products and then subtract the reactants that are added up. And this is how you find your enthalpy of your reaction. Q is used for experimental, but we're all talking about the same thing. You do use the number of moles in the balanced equation to help you figure out the total enthalpy of formation for each reactant. The sign of the delta H is important. If you have a negative delta H, that means you have an exothermic reaction. So if you had a sample equation, that means heat would be at a product. So you would have your reactant goes to your product, and you would have heat as one of the products. And then just the opposite for an endothermic reaction. If you have a positive delta H, that means it's endothermic. So heat would be a reactant, and so you would find that heat on the left-hand side. There are many different enthalpies, and so just know that they all mean the same thing, that it's the amount of heat. So whenever you see an RXN, it just means reaction. You might have a combustion enthalpy of formation. You might have melting something or freezing something, so the enthalpy of fusion. You might have the boiling of something, the energy it takes to boil a compound, and this would be called the enthalpy of vaporization, or going the other way, condensing something. So just know that all of these things, they're just enthalpies. You might be given a portion of a thermodynamics chart, and if you're trying to find your delta H, make sure that you look for the delta H column and pay attention to the units. So enthalpies are usually given in kilojoules per mole. And one thing you should know is that the enthalpy of formation for all the elements will be 0. So if you're looking for a certain formula and it's not on your chart, look and see if it's an element, because if it's an element, then you know that it's going to be 0. And that goes for the diatomic elements. So this is liquid bromine, Br2, and it has a enthalpy of formation of 0. Also, be very careful and pay attention to the states of matter. So they might give you H2O as a liquid or H2O as a solid, and they will have different values. When we're looking at these enthalpies, they typically use a little degree sign or a naught, and this is what it will look like. So delta H naught, and that means that we are at a standard state. So for a gas, that means that our pressure is exactly 1 atmosphere. For a solution, so if it's AQ, so aqueous, that means the standard state, we were at a 1 molar solution. And for an element, this means that our pressure, again, will be 1 atmosphere if it's a gas, and we are always going to be at 25 degrees Celsius or 298 Kelvin if we need a Kelvin value. These are the standard definitions of when these numbers are measured. So for thermodynamics, we're at room temperature, but know that the standard temperature for when we do our gas laws, the temperature is 0 degrees Celsius or 273 Kelvin. So that's a little bit different that you have to remember. Just know that gases like it cold, and so the standard temperature would be at 0 degrees Celsius. But for any time we're trying to figure out heats of reaction, that's going to be at room temperature, so 25 degrees Celsius. Let's go ahead and do a problem. So my delta H's are listed for each of the compounds, and I am going to take the sum of the heats of formation of the products and subtract the sum of the heats of formation of the reactants. I like to use brackets to keep all the products and the reactants separate from each other. Anytime you have something more than 1 mole, you need to multiply that heat of formation by that coefficient. Notice that oxygen's heat of formation is not given, and that is because it's an element. Doing my math, I get a negative 1041 kilojoules per mole. So this is an exothermic reaction. This is the amount of heat that leaves. And down here we have a little picture that shows each of the steps, what the change in enthalpy is. Let's go ahead and do another one. And remember, we're doing products minus the reactants. So working out the math, we get a negative 368 kilojoules per mole. Here's one more example, and I'm going to skip that our oxygen is 0. Make sure you watch your sign. A negative times a negative is a positive, and I get a negative 802.34 kilojoules per mole as my final answer.